measurements. These are hard, and I'm going to give you some feeling for that after I pay due respect to the surface measurements that have been made. So this is the only slide you'll see about surface measurements. And it's proper that I do that because these are the oldest of the measurements. They're the most, there are currently 44 missions flying that are making surface measurements. And they're used for land cover measurements, terrain, ocean mapping, all that sort of thing. And you probably know that what they do is look at sunlight that's reflected from the surface of the Earth. Right? That's what they measure. And the oldest of these are the Landsat missions. The first one was launched successfully in 1972, and there's been a continuous series of Landsat missions ever since, overlapping. And there is planned to, it is rather planned to continue with the Landsat continuation mission, which is being discussed right now by NASA, and the conclusion is that it will have to be another government-funded, just like all the other Landsat missions, where NASA tried to get the private sector involved in actually funding this and selling the data, but nobody would bite. But anyway, it's some parameters to think about and remember when I talk about other kinds of missions later. Landsat 7, which is the most recent one, is 2.2 tons. A standard kind of sun-synchronous low orbit, 705 kilometers, 98.9-minute period. It looks at the surface through these wavelengths, a couple in the infrared, but mostly you'll notice in the visible and near infrared. The thing about all surface measurements is that they have ferociously high resolution. Landsat 7 is 30 meters pixel resolution, 30 meters per pixel for almost the whole of this range. And they have roughly 6,000 by 6,000 pixel detectors so that they can look at a scene of 170 by 185 kilometers. So the reason they can do this is because the surface albedo of the Earth is very high, right? It's around 30% of the sunlight that falls on the Earth gets reflected. And so that's bright. And that means that they get very strong signals and they get very high sensitivity. And that's also the reason why people were doing this sort of thing a long time ago. So that's the story for surface that I'm going to tell you, and you can also ask me questions later. I don't know a lot about it, I'll admit right now, but I'm happy to talk about surface measurements because they are really the vast majority of spatial remote sensing measurements. However, I'm here to tell you about atmospheric measurements, and since I wasn't really aware of the background of the audience members, I thought maybe not too many of you had a chemistry background, or if you did, you probably didn't like it, and so maybe I would tell you a little bit about chemistry because that's relevant, highly relevant, as a matter of fact, to the kind of goals that one has in measuring atmospheric composition. So that's the atmosphere that you always read in textbooks. In the order of abundance, you have these gases. And everything with a star on it has two properties. One, it's a variable amount of it in the atmosphere, depending on anthropogenic activities, temperatures, pressures, locations, and so on. And the other thing is they're all greenhouse gases, and so they're important for those two reasons. And so one class of atmospheric measurements are aimed at measuring greenhouse gases in space. The other class of atmospheric measurements are aimed at looking at trace constituents, which are basically air pollutants. And the most important of these in terms of atmospheric chemistry I listed up here, and it's a highly personal list, but nevertheless I think most people would agree with me that sulfates, NOx, CO, and volatile organic compounds, as well as aerosols, are really the culprits in most air pollution scenarios, and so those are the ones we want to see. Now, likely you already know this, but I had to put it in. I just talked about chemistry. Now I'll talk a little bit about physics of the atmosphere, because it is important. The pressure curve here is on the left, and the temperature curve is on the right. And the troposphere, tropopause being, in mid-latitude, somewhere around 15 kilometers, is defined by a temperature minimum. And there's really only one property here that I want you to remember, and that is that the temperature decreases in the troposphere to this minimum, and then it increases again through the stratosphere. And that means that in terms of convection, the stratosphere is stable. The warm temperatures are at the top and the cold temperatures are at the bottom. And the opposite is true of the troposphere. The warm temperatures are at the bottom. That means there is an enormous amount of turbulent mixing in the troposphere, and that makes the chemistry completely different from the chemistry of the stratosphere. And that's relevant, again, when you're looking at this from low Earth orbit, which, as I said, is 700 kilometers. So you're looking through everything. But most of the time, if you're looking at air pollutants, you're concerned about the troposphere. And I'll say a few things about the fact that the stratosphere has similar molecules. Well, everybody knows there's ozone in the troposphere and in the stratosphere. And so you have to sort that out. The other thing to remember is that almost all the atmosphere is in the troposphere. This is the pressure, atmospheric pressure in millibars here. And so it turns out that about 90% by mass of the atmosphere is below 15 kilometers. So that's the chemistry and the physics, but I really try to bring this point home to people, especially when I'm speaking in public people who may or may not have a lot of education. This is a drawing to scale of the Earth, and the diameter 12,700 kilometers. And folks in the front can see there's a little red line here, and that is more or less, actually it's thicker than, but it's kind of to scale with the troposphere. So that's your 15 kilometers there. It's actually more like probably 30, but it doesn't, you get the point. It's very, 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 very thick in terms of distance. The satellite, as I said, sees through the entire thickness of the atmosphere, but we're really trying to find what's the composition of that red line here. And red line. And also, we have to be aware of the fact that the chemistry of the stratosphere, which is above that, it's 2 or 3 times the thickness of that red line. And it's different, but for the purposes of this evening's presentation, we're only going to talk about the troposphere. So what does 15 kilometers mean? Well, if you look at Google Earth and measure 15 kilometers from where we are right now, up here at Waterloo, that's Highway 86. I don't know, it's probably hard to see, but there's Highway 7 going off to Stratford in 86 here. And we're here at the University of Waterloo, and Highway 401 is there. And roughly speaking, well, actually fairly accurate, from somewhere in the middle of UW campus to 401 is 15 kilometers. So if you drove 15